Okay. Yeah, okay. So yesterday we had a look at the start of the Curry-Howard correspondence, which is this idea that types are really can be seen also as statements of mathematical statements, and then programs can be seen as proofs because we're in ACDA, where you're not allowed to do side effects without declaring it. You're not allowed to loop infinitely and so on. And so when you actually write a program, you know that it will compute an answer eventually. And the part of the correspondence that we saw involves the empty type, which is a modelization of what it means for something to be untrue. And we showed that in some cases, something are just blatantly untrue, and ACDA is able to accept your statement that any such proof, if it were to exist, could just be thrown away. We also saw how you could construct something manually that has the same behavior. So by exhibiting actually a function that does distinguish the two values that someone claimed were equal. And then just through computation, you could transport a value that was easy to construct into a value that was impossible to construct by using the equality proof that's invalid. Then we saw the explosion principle. So if someone claims that something untrue holds, then you can just do whatever you want. And then we saw that sometimes you need to put a bit more effort in proving that things are not untrue, because ACDA, if you tell it like it's not the case that plus and times are equal, will just not be able to come to a conclusion, because these two programs are complex, the program for plus and the program for times, and ACDA will not be able to see immediately that they cannot possibly be equal. So it's your responsibility to, from that assumption, derive a contradiction. And so here we applied 1-0 on both sides.
Yeah, I mean, if you think about it, how do you tell two functions apart? Do you find an example of some inputs where they give noticeably different outputs? And as these things want two numbers as inputs, that's an awful lot of possibilities for what the counterexample is going to be. So you can't really expect ACDA to go hunting for it.
And then so we started going back to like this correspondence, this Curry-Howard correspondence, by saying, okay, well, now that we know how to encode falsity, we can describe what it means to negate a statement. And negation is just saying, if that statement were true, we could conclude anything we wanted. And then we saw that you can, from a proof of a statement, prove its double negation. And this is just like flipped function application, right? Because this not x is a bit like a function. And then we saw that there was no hope for us to implement not double negation elimination, which is to say that if we know that it's not the case that something is not true, it's not the same as having positive evidence for that thing. Yes. So the example being that if you know that it's not the case that A or B is true, is not true.
Yes.
No, it's not the case that A or B is not true. That doesn't give you a bit of information on whether you should go left and prove A or go right and prove B. So you just know that if someone were to give you a proof that A or B is not true, you could derive a contradiction, but you cannot extract any information from that statement.
Yeah, it's just because you can't disprove that there are fairies in the teapot when you're not looking. You can't just like hold your eyes closed and pull a fairy out of the teapot.
Right. So thank you for the So implication is just a slight generalization of negation. So we said that we said that the negation of a statement was that if that statement were true, then we would be able to derive a contradiction. And implication is going to be similar. It's going to say that A implies B. We can model it as, if we know that A is true, then we should be able to derive a proof. Well, if we have a proof of A, we should be able to derive a proof of B.
Yeah, so the key thing to think of is that the type represents a proposition by saying what constitutes evidence for that proposition. And what we're saying here is, if to claim that A implies B is to say that if you were given evidence for A, you could produce evidence for B. It's exactly a function type.
All right, and then, I don't know if it's going to be provable in one direction or the other. But so, if we want to say that it's not the case that A implies B, we can combine what we've seen so far and say that not implies, I don't know, not and bottom. We don't have that many constructions yet, so there's only so much we can do. So this is saying that if you give me a proof that not implies the empty type, which is sort of absurd, right? Then I can prove anything I want. And this is just double negation introduction, because I spotted the pattern on the NAT. So I can just give any NAT as a contraproof. But this is not the most.
Maybe Guillaume, we should pause a little bit and say what is not doing here. So bottom is kind of a proposition, right? That's false. But not is kind of strange as a proposition. We don't normally think of not as a proposition.
Okay.
But you could think of it. I mean, it's the proposition which has lots of proofs, right? 0 is a proof that not is true. 17 is a proof that not is true. 12,041 is a proof that not is true, right?
Yeah, it's not a very interesting proposition. It just has lots of proofs.
Right, so alternatively, I use 0 equals 0. There's a unique proof, and it's a much more self-contained thing. But as we were saying earlier, not doesn't, like if you have a proof of the negation of something, you don't get a lot of information. It's just telling you that if you were to, at some point, acquire a proof of that thing, you could just dismiss it. So something that's maybe a bit more informative and a bit more constructive would be to instead have an element of 0, 0. Oh, we don't have pairing. Okay, so maybe this is future work. So instead of having not implies AB, one thing you could think of is have an A together with a proof not B. And this is, you should be able to prove an implication in one of the directions, because this is a lot of information, right? I'm giving you a witness of the kind of inputs you can use to feed into the A implies B proof to get a proof of B, and then I'm proving you that B is impossible. So you have a slightly more information than if you just have a proof that not A implies B. So thinking about refutations. Should we do conjunction here? Or is there something interesting to do with implies?
I think we should do conjunction.
So, so we saw that implication is the same as functions, basically, and conjunction, if you're thinking about the introduction rule, it's saying that, well, I can write it down, actually. Like this. I have a proof of A, and I have a proof of B, then I have a proof of A and B. Okay? So from the point of view of data, it's a bit like the pairing construct that we saw a few weeks ago, where we would put two values together if we wanted to return two values from a function, right? So this is exactly what we're going to do. And I guess. So if I have two types, I can define the type of evidence for the conjunction of A and B. And when is it true that A and B is true? Well, when I have a proof of A and a
You'll
proof of B.
need field.
Right. Right, so this is a fairly easy mistake to make. If you forget the field keyword, Agda will just assume that these are definitions you're throwing in as part of the records, and then you'll complain because you know that they are declared but not accompanied by a definition. So there should be more helpful error message telling you that maybe you forgot the field keyword, but that's usually what happens.
That's right. So yeah, Agda's notion of record is a little bit helpful in that it allows you to specify not just what the provider of the record must give to make a record, but also what auxiliary operations can then be constructed from that stuff. So you can bundle up kind of defined fields as well as declared fields. And that's kind of cool, but it means that this kind of cock-up happens. Right.
All right, so let's see my point. So I can't remember.
Why don't we do something simple? A implies A and A.
Oh, yeah, okay. So I can write the diagonal. So if I have an A, if I have a proof of A, I can prove that A implies A. Good. Oh.
That's
And yep. I mean,
You want to do it a little bit slower, maybe?
sure. So I can bind my proof, right? I have a first argument, that's my proof. Then I have a conjunction here on the right hand side. And we say that to prove that A and B is true, you need to prove that A is true and that B is true. So here it's the same type, so it's going to be fairly easy. And when we define this record here, we gave a name to the constructor as like the infix comma, so that we have a notation that's reminding us of Haskell. So I can use refine to take a step. Agda is like, sure, there's a single constructor for these kind of values, so I'm going to use it. And then we have two separate goals, each of them saying, please prove A. And so I can just use my proof of A. Maybe I should call it proof of A. We can swap. If we know that and AB, then we know that and BA. So here you can make some progress in various different ways. So the first thing you could do, it's the usual thing we do when we have some data as inputs, we just pattern match on it to expose the constituting parts. So I could split on proof AB. This is giving me horrible names, but. And because the single constructor is comma, with a first component of type A and a second component of type B, I get exactly this. So if I look at the goal, I got a proof of A of type A and a proof of B of type B. And now the goal is going to be the same as above. I can refine to use the only constructor, and then Agda should be able to figure out what the parts are. Alternatively, because we've used the records, we've automatically defined projections out of it. So you could say, okay, I have a proof of A and B, and I want a proof of B. Well, I can take the second projection out of it. Second A, B.
You will need to open
Oh, Yeah, well,
Yeah.
okay. Maybe I should open it.
Right.
And then for the second part of the proof, I want a proof of A. I have a proof of A and B. I can project out the first component by using first.
Right. So this is another difference from Haskell, that the projection functions for a record type are not automatically in scope. And you're allowed, and that means you're allowed to use the same names for projections of different types because they're not in conflict with each other unless you bring them into conflict with each other. So that open AND says, actually, I do want those projections to be in the top level scope.
Okay.
Right. Okay, yes.
So as I was saying earlier, there's a more informative notion of refutation, of implications. Instead of just saying it's not the case that the implication holds true, you could prove that the premise is true, but the conclusion is false. So this would be not implies A of B. A and B is the AND of A and not B. Of course, this is not super satisfactory because here we're back to not. So ideally, you would want this more constructive notion of negation to be used also for the refutation of the goal, because if you have an application with multiple premises and then a conclusion, of course you want to be as informative as possible all the way through. And so I could prove this one times prove not, etc. I could prove this thing. And now you see that how do I prove this? Well, I need both a proof of the premise and a refutation of the conclusion. The proof of the premise is, again, very simple. That's by design. And then the conclusion, I need to prove the negation of the empty type, which, if we normalize it, is the type of the... Oh, wow, okay.
You got pay your money, take your choice.
No. Agda decided to be strict in its argument, but you could also just return it immediately. All right. Does someone want to do disjunction?
I guess I could do. Okay. So conjunction and was a record type with two fields. To give a proof of A and B is to give a proof of A and to give a proof of B. Likewise, disjunction is going to be a data type with two constructors. And I guess I will have the French keyboard syndrome. What do? I pick it. It pains me to pick English. Or A, B in set is itself a set where, and there are two ways to prove an or. You can either be in the left case, which takes an A and gives you a proof of or AB, or you can be in the right case, where you give a proof of B in order to establish or AB. Right, save, load, everything in color. So, what shall we prove involving or? Let's prove a distributive law. How about that? Right, so for all A, B, and C, if we know, what do we want? If we know the AND of A and or BC, then we know that we either have A and B, or we have A and C. Make sense? All right. And if you're thinking that's a lot like the distributive law of multiplication over addition, you're not wrong. Right, so I've got some input, which is a pair. All right, so let's look at what we've got. We've got something which lives in some AND type, so I'm just going to pattern match the hell out of this, basically. Right, and it chooses terrible names. I'm going to call them A, B, and sorry? Oh, right, yes, that's an A, you're right. I'm going to call this A, and I'm going to call this Bork. Okay, but it's not going to stay called Bork for long because I'm going to pattern match on it. And then I get things which are unhelpfully called X when I want this one to be called B and that one to be called C. Okay, reload. And you can see that we have exactly an A and a B. So if we're trying to figure out whether to go left or right, there's a pretty good clue lying around in there. Can we see how to do it? Even Agda can see that it ought to go left in that situation. And likewise, here, Agda can see that we ought to go right. Okay. Does anybody else want to do excluded middle, or shall I stay in the hot seat? Thanks.
So now we have all of the language in order to talk about basic propositions, right? So we have and or and implication and negation and falsity. And I guess we haven't introduced truth, but we use any type which has an inhabitant, such as natural numbers, stands for something true, right? Because it has a proof.
Yeah, we quite like the record with no fields, because it's really easy to give all the fields of the record with no fields.
So should we just introduce that maybe?
That's it, yeah.
Just for tidiness. So usually we call this top for truth. And we're saying this is a set. And we like to give it a constructor. We usually call this TT, so tradition. And what does it mean?
Yeah, it's traditionally the constructor of the Boolean type for true. Yes.
What does it mean to prove this?
Yeah.
Well, we have to fill in all the fields of this record, right? But there are no fields. So, well, there's two ways we can do it. We can do it with record like this. So here between the braces, I've put all of the fields of the record, which are none. Or I can use the constructor, which is just a shorthand for the same thing.
Or there's even another way of doing it.
Okay, what's that?
To say you don't care what this record is.
Okay. So I can also say, let's figure out what this has to be by unification.
Yes.
So put the underscore, which tells Agda, you find out what this is, right? So if I try to say, I want to have a natural number, then of course I can say 7 is a natural number. I tell Agda, you find out what this is, then Agda is not going to be happy. This is yellow because Agda can't figure out which natural number I want here. There's many to choose from. So that's why this is colored yellow, and we should not be happy with this. Because Agda can't find a solution, in this case because there's too many, but it could also be because there's too few, right? So yellow means that it's not uniquely determined, and we should explicitly say which one we want. Whereas here, there is no yellow because there is exactly one inhabitant of this type, which is namely the one given by the constructor T.
Yes, and Agda literally reasons, oh, to figure out a record type, I have to figure out all the fields. Done!
So you could even go even further. So if you have x, which is a proof on top, then you could try to prove that x is equal to tt, right? And so this is my goal, but if I fully normalize my goal, okay, it doesn't help.
Then you will get a beta normal form.
Yeah.
Aha. But
if I try to say REFL is a proof of this, then Agda's actually happy. Because again, everything of this type is equal to, X has the same projections as TT. Right?
yes, the way Agda compares two records for equality is to compare them field by field. Done! So,
Which is very useful for the AND constructors. It means that two proofs of AND are the same if the first projection is the same and the second projection is the same. But here we have this kind of special case when there are no projections. So it's very easy for all of them to be the same. Okay, so that's how this is kind of the canonical true proposition, right, which has exactly one proof, which is very nice to work with. And here's a non-canonical true proposition, which has many, many proofs. But okay, so what is the law of excluded middle? This is usually, this is a name for the statement that if you have some proposition P, then either P is true or not P is true. So for every proposition P, either P holds or not P holds.
is this some kind of Swedish protest against Danish kings? I mean, be or not be, surely. Yes.
That is the question. Okay. So from ordinary propositional logic, again, we are kind of used to this being true. Right? So let's see if we can prove it. Okay, so our goal is the law excluding middle. We normalize that. That means that for every B, we have to say if B is true or if not B is true. Okay. Step one is easy. We are given a B. So let's take a B. I'm going to put it on the left. Step two is hard because now I have to give a proof of an OR, which means I have to decide if I want to go left or if I want to go right. But that really depends on what B is. But B is just a set, it's just a type. So I can't pattern match on B because there is no principle to list all of the types, right? So I don't know if B has a proof or not. If I knew it did, then I would go left. If I knew that it's impossible for B to have a proof, then I would go right. But I don't know when I really have to go different ways depending on what B is.
Yeah. Also, B might encode some undecidable proposition.
Yeah.
In which case, you're going to be hard pressed to jump one way or the other.
So B could be the proposition that Connor's favorite Turing machine holds. In which case, if I could give a proof of this, then I would solve the working problem for Connor, which would give me a prize.
Right. Yes. So basically, the law of the excluded middle says there's a fairy in the teapot who knows an awful lot of stuff and can give you a bit of data whenever you ask any question. Yes.
Okay. So that's one thing we can't prove. Earlier up here, we saw another thing that we couldn't prove, right? Double negation elimination. So you could now wonder if these are related somehow.
Yes.
You want to run the disk here.
Oh, do I?
This is a job for two people.
A horrible proof. But so the punchline is basically that they're equivalent. But
Now Fred's done a dirty trick.
did I want to do this?
What you want to do, you want to prove the double negation of.
Yeah, that's what that's what I was going to say.
You're going to
If
get
people
into,
want to have fun,
you're going to get into universe level hell.
am I?
Yeah. um, yeah, right. Okay. No, this will work out fine. Right. I think.
So, well,
This should be the easy one.
yeah, I think I
Yeah.
won this one, and then we can leave the other one as homework. Right. So what Connor was suggesting, and what I was thinking to tell you, if you want to have some fun,
Yeah.
and before next week,
Yeah.
you can prove this.
Well, that doesn't even type check because of universe levels.
All right. Okay. Well, you can prove that it's. Oh,
Yeah.
that if someone claims the law of excluded middle as not true, then you can actually prove them wrong.
Yeah.
Uh,
But yeah, here we go. This will be fine.
but let's do this one. So I have the law of excluded middle. I have a B, and double negation elimination is telling me that it's not the case that B holds. So that's not B. Okay. And so the intuition here is that, okay, I should normalize. Let's normalize. I never know how to show the goal. There we go. So the law of excluded middle is telling me that for any set, it will either hold or it will have a refutation for it. But the argument that we pass to double negation elimination is telling me it cannot be the case that B doesn't hold. So intuitively, I'm going to be able to dismiss this branch as being an impossible branch, which is what we've been talking about earlier with like the explosion principle, right? If you get your hands on a proof of the empty type, you can just do anything you want. And because I can dismiss this dead code branch, essentially, I am guaranteed to be in this one. And so I will be able to extract a value from this side. So let's do it this way.
It's now the time to introduce with.
Oh, okay. I was going to do something naughty, but
Maybe the top level thing is a good thing to do.
oh, okay. Well, you don't know what you're asking for,
You're
but
going to do something else.
as a user of the so Agda is a fairly small language, and case does not exist in the language, but turns out you can emulate it with some magic definitions that are in the standard library. Because why define it? No, why include it in the language if you can just define it? So the idea here is that I'm going to call the LEM oracle on B, and it's going to tell me whether B holds or not B holds. And from there, I will make some progress. And then I can do this. Okay. So this is a pattern matching lambda. So it's a bit like lambda case in Haskell. It's taking its argument, and because of the where here, it's immediately splitting on it. And then you go to a new line, you sort of indent the block a little bit, and you're listing the clauses one by one. So here I've just listed a single pattern P, and I'm going to split on it. And I have two possibilities because this argument at type B or not B. So here I have a proof of B, and here I have a proof of not B. Okay. So in the left branch, I'm really happy because I got my hands on the B and I need to prove B, so I can just return it immediately. And in the right branch, well, I still need to prove B, but now I actually have two assumptions that are contradicting each other, right? It's both the case that B is not true, but also that it's not true that B is not true. So I can just explode with not B applied to B. And just dismiss this entire branch. So you can, ooh,
Yeah.
talking about explosion, I could throw the grenade back to...
Do it the other way. It's fun doing it the other way around.
Yeah, well, I was going to throw the grenade back to Fred.
Yeah.
I don't have a microphone.
Right. So yes. So you see, Lem is the name of the fairy in the teapot, and we managed to prove double negation elimination by asking Lem about B.
Okay.
Right.
So before I start thinking, I just be given an argument of type double negation elimination, so I'll just introduce that on the left. I have to prove Lem, and that means that for every B, I should do something. So take a B on the left. Okay, and then I'm in the same bad situation as before, right? Where a priori I now have to decide, do I go left or do I go right? Which I couldn't do. So I don't know if this Turing machine holds or not, right? But I have more things now. I've assumed double negation elimination, which says that if I want to prove some property B1, then actually I can get that if I can prove it's double negation only.
Yeah.
So I don't want to apply this to B. I could, but then I'm kind of committing on going left here, right? But if B is false, then that's the wrong move. But I can instead do B or not B as my...
Yes. Oop.
Oh, not B.
Yeah. So double negation elimination is a classical mathematical form of procrastination. It says, you want a bit? I can't give you that bit right now. I'm going to put off this decision.
So if I can fill this hole, then I will get the thing I want, right? So now the question is, can I show this thing with lots of knots and lots of implications? Well, I can just follow my nose for now. Or maybe I'll take it slow. So I'll introduce something of the type I want in a where clause. Then I can see what I'm doing. Okay, so now I follow my nose. I get given some argument.
We really want that to be called not Borb, don't we? Oh, not B or not B, actually. Not B or not B. Yeah, the hyphens don't really cut it. Anyway.
Yeah.
Yes, fine. That's classic Agda programmer. Let's just make a perfectly ordinary identifier with lots of funny symbols in it.
Okay, and then I want to prove false.
Yeah.
I suppose I have a way of proving false.
Yeah. So the thing about when you have a negative assumption in your context, that gives you a superpower. At any point you're in the middle of a situation you don't like, you get to say, I would rather be proving whatever it is that's negated here, right? You know that if only you could prove the thing that you know is false, you're done. So you can say, you know, I'd rather be proving B or not B at this point.
And it looks like I'm back to where I started. That's not good. But actually, I know something more now, right? I know that this is false by assumption. So going left seems like a bad idea, because then again I have to prove a B. But if I go right, then I get given a B, so I know even more things. And if I know B, then I should know B or something else, which I'm assuming is false. So then things should explode, right? So I'm going to go right. Then I have to show B implies false. So I get given a B.
Right.
And now I have to prove false again. But actually here, I have in left of B, which is a proof of B or whatever you want. But I also know that B or this particular thing is false. So
right.
if I apply this to that, I have a proof of false.
Right. So this is the thing that is just such cheating, right? Let me get my pointing device. Here we had to prove false, and we used our assumption to say, I would rather be proving B or not B. And so we made a start on that. We said, okay, I will go right. I'll prove not B. Thank you for giving me an assumption of B. Now I have to prove false. Oh, I would rather be proving B or not B, except this time I'll go left. Right? You get to make a failed proof attempt, pick up a load of swag, and then decide to do something completely different. Only you've still got the swag. You know, it's pure bank robbery. I mean,
So in particular, what this shows, if we believe that we can't implement lem, because then we could decide if Turing machine fault or not, right? Then this shows that we can't implement double negation elimination either, right? Because they imply each other. So if we could implement this, then we could implement lem. But we said we can't implement lem, so we can't implement this. So here are two principles that we don't have access to, but they could still be interesting to reason about, in particular because they show that certain things are not possible for us, right? Because it's too good to be true. If we could do something, then that would imply one of these things, but we know that they are not implementable.
Right. And this is not really in conflict with like what you learned about like logic for things that are at 0 volts or 5 volts. When everything's testable, then you do have a perfectly workable law of the excluded middle. You know, 0 volts, not 5 volts. There's no 2.5 volts in that picture.
5 more minutes.
Yes.
Yeah, and if you stare at this for sufficiently long, you might notice that it looks a little bit like this. I mean, there's an extra universal quantification. So the idea to prove this, if you want to have fun, is probably going to be fairly similar, where you start proving something just as a way to acquire more premises, more assumptions that you can then reuse in the different part of the proof. Right. So I think you can do De Morgan's laws yourselves. Maybe this is so you know what they are. You can try to prove them. So they're not a bit. So when they're formulated about booleans, right? You're saying I don't know. When you have them about booleans, you might say something like BC, not B and C is not B or not C. So of course for types it's going to be different. So you're going to be using our type constructor not or type constructor and instead of equality it's going to be double implication, right? You're going to want to prove that one implies the other and the other way around, just like we did for the law of excluded middle and double negation elimination. So you can try to do that and you'll find that in some directions it will work and in others you won't be able to, because the intuition is that in some directions you'll be using a really strong like refutation, for instance, to prove that something is impossible. So you have positive evidence to dismiss something, whereas in the other direction, you just have the information that something is impossible, and then you need to come up with bits of information. And bits don't appear out of nowhere. You usually grab them somewhere and then repurpose them for something else. So if you look at this one, for instance, on the right-hand side here, you have one bit of information, at least one bit of information, telling you whether the left one or the right one is true. But on the left-hand side, it's just telling you that it's not the case that both of them are true. So there's nothing here that you can pattern match on to get some information. So it's probably the case that going this way will not work, but going that way will work. But something that's somewhat interesting is that we've seen a lot of results about impossibilities. So we cannot have the double excluded excluded middle. We cannot have double negation elimination. But it's not completely true. We cannot have them for all of the types. But we can then restrict our domain of discourse to precisely the types for which it is true. And then we recover some good properties. So the fact that the De Morgan laws and so on are working in both directions. So this is the food for the cliffhanger sort of thing. We can define a new notion, which is a notion called decidability. And we're saying that the type B is decidable precisely when you can form a proof that B or not B at that time. And then if you restrict your domain of discourse to decidable types, you can prove that in deck. For instance, if B is decidable, then I'm not going to be able to reuse DNE, am I?
No, you're not. Because it includes the...
Yeah, the quantifier. Then it is the case that from all right, if I know that my type B is decidable, then I can use double negation elimination on it to actually produce a value from the double negation here. And I think I might not want to implement it.
Well, you kind of did
it's
further up.
Yeah, it's basically this, right? So you're using the decision procedure to tell you whether B is inhabited or not. And then you're using the assumption that it's not inhabited to dismiss the impossible branch. Yeah.
Should we do a little bit more decidable things next week, maybe?
Okay.
Yeah.
It's good to give some examples.
Yeah. LPO, maybe.
Yeah, or even just like testing whether two numbers are equal.
Yeah.
That kind of stuff. And in particular, these decisions play